What is a node? There will be question. What is a node?
Terminal.
When they no terminal, that means there is another thing that we call junction, node, and then we have branch. Do you conduct branch current analysis, mesh current analysis?
No, not yet.
There will be, in the following classes, there will be mathematics on mesh current analysis, branch current analysis, and other things. So the thing I am going to talk about the node, because the Kirchoffs current law is basically you can apply to somewhere a node. So node is there should be more than two terminal. That means one terminal is this and this. So once we have one more additional terminal to this node, to this one, then it becomes a node. This is called node. Okay. We have more than one terminal, two terminal connected to a point, then we call it node. So that means in a node, the Kirchoff say that in a node the incoming current is equal to always outgoing current. The sum of incoming currents will be equal to sum of outgoing currents. So if you look at something like that, I guess I have given this circuit here. So that means we didn't go for the experiment, just okay. So think about this.
You said only calculate the current.
Okay, listen. So that means this is one node, this is another node, because there are more than two components. Okay. So if we I define that here we have I4 flowing this way, and this is the 5 ampere current. So what should be the direction of, okay, if it is 10 ampere in this direction, then in this node the incoming current, sum of incoming current should be sum of outgoing current. So if we add incoming current, which is 5, I don't know the value of x right now, and the direction as well. So if you count this node, and 10 ampere is outgoing, right? So outgoing is 10 ampere. So incoming, summation of incoming is equal to summation of outgoing. So if this is happening, so incoming current, listen, incoming current we count is as 5 ampere, and outgoing is 10 ampere right now. So listen, as 10 ampere is outgoing and incoming is 5 ampere. That means the additional amount of current that is flowing here in the outgoing direction should be obviously in towards the node, right? So that the direction of this x would be inward, right? So 5 ampere plus x ampere would be equal to 10 ampere. So x ampere is like 10 minus 5. That results 5 ampere. So that is how we can find out the unknown current to a node or to a particular junction using this law. Okay, so that means the equation comes like, if we would say that is I1, nothing there, right? So let me bring a marker. This one. So if we have that one as I3, that one as I1, and this one as I2. So then if we apply Kirchoff's current law here, then we would say I1 plus I2 would be equal to I3, right? If we would have more than this, like that, then maybe there is another current, there is another current. Then this time it would have been that is I4 and I5. Then I3 plus I5 would have been the outgoing, and additional I4 would have been added with this. So I4, I1 and I2 was incoming current, and I3 and I5 was outgoing. So that is how it should be equal always, right? Or you might say the sum of incoming current and outgoing current is equal to 0. Then it will be like this: I4 plus I1 plus I2 minus I3 minus I5. That makes 0. Similar thing. Or you can say incoming current is equal to outgoing current at any particular node in any circuit. So there is nothing like So that means what? The nodes are not basically using any current. Whatever it takes,
Transferring.
it will deliver that. Whatever it takes, it will deliver. So there is nothing that is in it, right? So let's draw the circuit. Okay, I'm giving you one thing that might be that sort of question might be in the exam. That is, if the circuit is like this, if the circuit looks like this, listen. And in the previous class we learned that what happened to the voltage once we add some potentials to a circuit. What happened to those potentials? So we have seen that those potentials basically drops across different resistive element in that circuit. In this experiment we learned, Kirchoffs talks about the current as well. He said that the current that is flowing to a circuit, what happened to that? To a particular node. The current doesn't used anywhere. Voltage has been used, but current will always come back, right? If it is entering some currents, there will be all leaving. There will be no current left in this particular node or in anything. But voltage will be dropped. Okay, listen. So if the circuit looks like this, tell me. Yes. Okay, let me explain. 5 volt. So that makes 5 ampere current maybe flowing to this way. That is I1, that is I2, and that is I3. What is the value of I1? What is I2? And what is I3? Can you tell me?
I1 is 5.
Sir, I2 is 5 ampere, I1 and I3 is 0.
Yeah. So all the current that will be flowing through this way.
Short circuit.
Because of the short circuit. So there will be no current flow in between this two terminal, right? You understand? So that means we always have say that is in a short path, that when there is a short path, there is no value of other, I mean there is no use of the other resistance which is connected. So you have to make sure the circuit is never a short circuit. This time it's a short circuit, even though there are other resistors connected. So you cannot say that once the resistors is connected, the circuit cannot be a short circuit. But circuit can even be short circuit if we have resistor connected. Right. So this time also we could say the incoming current is equal to outgoing current, because if you see this node, the current is incoming and all the currents that outgoing. So in this node, this outgoing current will be 0, right? So even though there are 3 terminals, but the current comes in from one terminal and gets out from one terminal because of the short, right? Okay. Then come to the circuit diagram. We draw a circuit diagram for this experiment, which will look like this. We have a common resistor, is this, and there will be 2 other resistors. So we'll add an ammeter to measure the total current, which will be I1. So I1 will be flowing this way, or I. That's the total I. And we'll prove one more thing, that is the current divider rule. Right? So you have learned the current divider rule. So today we'll also examine the current divider rule, whether it is true or not. Okay. So that's the ammeter will be used for measuring the current that is passing through this branch. And there is another ammeter that will be used for measuring current across, through this resistor. So then both of them will be added together and we'll come back to the ground. So you might say that's the verification of current divider rule, or as well as Kirchoffs current law. Kirchoffs current law. And you also say that's the verification of current divider rule. Verification of current divider rule. Divider. So current divider rule says that the branch current, okay, we have two branches here. That one branch current is I1, that is flowing this way, and another branch current is I2, that is flowing this way. So I1, I is the total supply current for now. So that's the resistor, that's the R2, that's the, okay, think about that's R, that's R1 and R2. So the total, okay, the branch current, any branch current, maybe that's R2. Oh, sorry, I2. The current flowing in this branch is I2, right? So this I2 is equal to, will be the total current, supply current, IS, into opposite resistor. What is the opposite resistor?
R1.
R1. So that's R1.